Hello, my name is Sina Sajadi, and this is the virtual presentation of our Case 2021 paper, Stochastic Image-Based Visual Predictive Control. Motion control of robust and unstructured environments is a challenging task. The utilization of cameras as information-rich sensor shows promise. In this context, vision-based robot control, also known as visual servoing, refers to use of visual sensory data to control the motion of robot. Visual servoing systems exploits an image taken by camera to measure the error between its current and desired pose. In this technique, the image obtained via a single or multiple cameras taken from environment, object of interest, or robots provide the sensory feedback to the motion servo control of the robots. The existing visual servoing are classified based on their underlying control architecture and error function definition, which can be categorized as image-based visual servoing, position-based visual servoing, or the amalgam methods of hybrid visual servoing. Advances in model predictive control has provided the essential framework to formulate vision-based control as a constraint optimization problem. The goal of this class of visual servoing controllers, known as visual predictive controllers, is to provide a systematic way to take input, state, and task constraint into account and accomplish visual servoing tasks in an optimal fashion. However, a systematic procedure to handle uncertainties has not been fully addressed in the literature. Multiple factors can be the root cause of uncertainties in a visual servoing system, such as imperfect system models, measurement noises, and exogenous disturbances. Some uncertainties in the visual servoing system may have deterministic nature, for example, camera calibration error. Adaptive visual servoing methods have been proposed to compensate the deterministic uncertainties in visual servoing. However, many system uncertainties involved in visual servoing tasks exhibit random and stochastic behavior, for example, noisy camera measurements. Robust visual predictive control methods have been proposed as a variation of VPC that provides an improved control performance in the presence of system uncertainties. RVPC methods generally employ a bounded deterministic uncertainty model to robustify VPC by taking worst-case uncertainty realization into consideration. Although RVPC techniques provide a robust and constraint-compliant solution against system uncertainties, they exhibit an unnecessarily conservative performance. In fact, the knowledge about the probabilistic nature of the system uncertainties is being neglected in RVPC. Alternatively, stochastic visual predictive control approaches have been introduced to exploit the knowledge about the probabilistic nature of the system uncertainties. In contrast to RVPC, that considers the worst-case scenario of the uncertainty realization, SIVPC accounts for the most probable uncertainties that system is likely to encounter. As a result, SIVPC method provides superior control performance compared to that in RVPC. SIVPC algorithm allows to systematically trade off between the conservatism of the solution by addressing chance constraint and allowing an acceptable probability of constraint violation. This paper proposes a set of stochastic image-based visual predictive controllers to enhance the accuracy and constraint compliance of visual servoing tasks in the presence of uncertainties. In our proposed approach, first, the statistical models of measurement noise and model error are developed. Next, a computationally tractable approach is proposed to propagate the system uncertainties in the finite future horizon. Finally, a SciVPC algorithm is designed based on information provided in prior steps. Owing to the stochastic system uncertainty propagation model, a SciVPC provides a compromised solution between admissible probabilistic constraint violation and system performance. The block diagram view of the proposed control method is presented. The robot camera control plant, the stochastic visual predictive controller, and an extended Kalman filter as an optimal system observer can be found on the diagram. In the next slide, we will take a closer look into composition of each of these subsystems. The underlying linear state space model of the robot camera setup can be formulated by successively linearizing forward kinematics of robot and camera projection model in each control sequence using system Jacobians. The system linearization is necessary to reduce the computational load of VPC in real-time implementations. Also, the additive system uncertainty and measurement noise is considered to be zero mean with known covariance and normal distribution. As the measurement noise and system model uncertainty are considered to be additive with Gaussian distribution at each control step, an optimal estimation of state mean and error covariance can be estimated using the extended Kalman filter. The control cost function, which should be minimized over the prediction horizon, is formulated as the expected value of the summation of three different objectives associated with state error, system input, and terminal cost. The corresponding weighting matrices are Q, R, and P. The optimization results to find the optimized control input sequence U. A sequential quadratic program was employed to minimize the defined cost function and to handle the probabilistic test and input constraint. Also, the error associated with the state prediction is propagated through the following equation in the robust horizon, which is usually chosen to be shorter than prediction horizon. The propagated error would later be used for constraint handling and proving the performance. The constraint to be handled during the optimization procedure can be expressed as follows. 1. Control-related constraints such as actuator saturation boundaries, which can be modeled as linear constraint and manipulated variables. 2. The probabilistic state constraints can be expressed as the following probabilistic linear constraint, where M and N are imposed by the camera's field of view and P is the probability of constraint violation. The probabilistic linear field of view constraint can be robustly transferred to deterministic form using Chebyshev's inequality equation and result in the equation as shown. Our simulated experimental setup includes a 6-stuff Denso manipulator equipped with a Logitech USB camera under in-hand configuration. Some control parameters and system configuration are presented in this slide. In this set of simulation, we're comparing performance of classical image-based visual predictive controller against proposed stochastic scheme. Scenario 1 represents the performance of classic visual predictive control simulated under the influence of measurement and model uncertainty. The graph on top left represents the motion of the robot with respect to target. The top center graph shows the motion of the camera. The bottom left is the control joint angles, and the bottom center is the position of the features perceived by the camera at each instance of time, along with the initial and target feature poses. And finally, the two graphs on the right shows the error of the current and desired features in the image plane. As you might have noticed, since classical visual predictive control does not take system and measurement uncertainty into consideration, the feature points might leave the field of view boundaries of the camera, and this problem can lead to instability and failure of the visual servoing system. In the scenario 2, the proposed stochastic visual predictive control is controlling the visual servoing system under the similar configuration to scenario 1. In order to address the problem of features leaving the field of view of the camera in presence of uncertainties, which in many cases lead to failure of the visual servoing scheme, the proposed SIVPC scheme takes the statistical information of the existing uncertainties into account to limit the probability of losing feature points. As can be seen in this graph, the stochastic visual predictive control algorithm is keeping features a probabilistic safe distance away from the field of view boundaries. This way, the probability of losing feature can be set and tweaked as a control parameter. In this set of simulation, the allowed constraint violation is set to only 2%. The graphs on the right show the propagated error covariance and mean of predicted states. The solid line represents the state mean, and each color band shows one standard deviation of the propagated uncertainty. Each graph on top and bottom shows uncertainty predictions in one direction in the image domain. With the constraint violation probability set to 2%, the controller is keeping states almost 3 standard deviation away from the boundaries. The graph on top right shows the manipulated variable, which is angular velocity of robot joints. The velocity compared to the set limits. Finally, the graph on the bottom right shows the error of features in the image domain, converging to 0, meaning that the features finally reach to the target state. Stochastic image-based visual predictive control as an efficient method to handle image constraint in presence of modeling and noisy camera measurements was formulated and simulated on a 6 degree of freedom Denso robot model. Our proposed algorithm provides the systematic framework that takes an acceptable probability of image constraint violation into account. The advantage of this method over the classical image-based visual predictive control method was shown by simulations. The results demonstrate that the constraint violation problem was successfully addressed under an eye-in-hand camera configuration. Incorporating other task constraints such as kinematic or dynamic and actuator and physical constraint will be carried out in the future. Also, we will be investigating the learning and adaptive methods to capture system and measurements uncertainties in real time. At the end, we would like to thank our sponsor for supporting this paper, and I would like to thank everyone for watching this virtual presentation.